Well, so far in Chapter 5, we've looked at heat energy with the fancy name enthalpy. And we've said that a process, in this case a reaction, where two things come together to make one, has a particular delta H, triangle meaning change, H meaning heat energy, known as enthalpy, is equal to a negative 100 kilojoules. Energy, of course, is measured in joules or kilojoules, the negative sign meaning that it's an exothermic process, or energy is given off from the system to the surroundings, or energy is formed in this case, because it will be a product. And the numerical value gives you the magnitude, how much energy is either released or taken in. We've looked at how to find this enthalpy. We've looked at how to find various amounts of substances based on the enthalpy. And then we looked at a way to find enthalpy using an equation Q equals mc delta T. Q, of course, is just another fancy letter that means H, or heat at constant pressure, as long as it's performed at constant pressure. And then this equals mass times the specific heat capacity times the change in temperature. Now, in this particular video cast, we're going to look at another way to find delta H. And so the other way to find delta H is using something called the enthalpies of formation, or delta H, with a little circle in the upper right-hand corner and a little F in the lower right-hand corner. So, in this video cast, we'll look at what this means and how to find it. Pause the video now and make sure that you have a notebook, a pencil, and a calculator so you can follow along. Alright, so enthalpies of formation. Well, there are extensive tables that exist for calculating the heat energy of various processes. For example, there are lots of enthalpies of vaporization for things that go from liquid to gas. How much energy does that take? There are extensive tables of enthalpies of fusion for freezing of various things, or going from solid to liquid or liquid to solid. There are lots of tables or lots of calculations already published that have the enthalpies of combustion, or things that get burned, and how much energy is released or absorbed when things are combusted in oxygen. Well, today's topic is another tabulated value, and these are called the enthalpies of formation. The enthalpies of formation are the measurement of the change in energy needed for 1 mole of that substance when it's formed from its elements. So a little bit of what the letters mean. First of all, triangle stands for change, and it actually symbolizes the Greek letter delta, which means change. So sometimes it's called delta H, meaning change in H. H, of course, stands for enthalpy, or heat at constant pressure, heat energy. F stands for formed from its elements. So the little F right here means formed from elements. And the little circle up here stands for standard conditions for these substances. Standard conditions meaning 25 degrees Celsius, 1 atmosphere of pressure, 1 mole of the substance, or a 1 molar solution. And so when we find the enthalpy of formation of something, we always find it for 1 mole of that stuff, that amount. Here's an example. Here's carbon forming with hydrogen and oxygen to make this substance right here, which is known as ethanol. Ethanol, of course, is a substance that's in your gasoline. It's also the alcohol that's in beer, wine, and liquor. The enthalpy of formation of C2H5OH from its elements is negative 277 kilojoules. And so this thermochemical equation would have delta H after it, negative 277. And this happens to be only okay at 25 degrees Celsius. And for this particular chapter, we'll never look at any other temperature other than 25 degrees C. Now, the states of matter are very important, because at 25 degrees Celsius, carbon is in a solid state, and it happens to be in an allotrope called graphite, as opposed to something like diamond. Hydrogen is a gas at 25 degrees Celsius, oxygen is a gas at 25 degrees Celsius, and ethanol is a liquid at 25 degrees Celsius. If we change those states of matter, then this enthalpy would change as well, because remember, enthalpy is a state function. It depends on the state of the substances that they're in and what state they are changing to. Well, Table 5.3 in your textbook, if you're using the 13th edition of Brown-Lemay, and Appendix C of that textbook have extensive tables of standard enthalpies of formation. And you can see lots of different substances listed, their formula, and then their delta H right here. Now this is a small table compared to how many things we actually really know, and we can look at hundreds more just in Appendix Table C, which is on page 1100 if you're using Brown-Lemay's text edition 13. But you can see here that they list things like barium and then various substances that are composed with barium, and then they have the delta H listed right here in a column. And then here's another substance and those delta H's. And then over here we have many more, and over here we have many more as well. So you might have to look these up in the back of your textbook. And since you're always allowed to use open book and open notes, you should be able to look and find those when you're asked to need the numerical values. So here's another example problem. Write the enthalpy of formation equation for CCl4 liquid. Carbon tetrachloride is a good organic solvent used in the laboratory. So first we have to take its elements, carbon, and then we have to take its element, chlorine, and write them in their elemental form. Remember, chlorine is one that's diatomic, so you write it as Cl2. And then we put CCl4 as a product. And then make sure that you put the phases of matter at 25 degrees Celsius. Carbon, of course, is a solid. Chlorine's a gas at 25 degrees Celsius. And then CCl4 told us to find the enthalpy of formation for that as a liquid phase. Now we'd have to put a 2 right here to make sure that we have 4 chlorines, just like 4 chlorines. And then at the very end, we'd put the delta H equaling negative 139.3. And how do I know it's negative 139.3? Well, I look it up here, and I can find carbon tetrachloride underneath the listings right here. And it's kind of small, but you follow it across right here, and it says negative 193.3. So that has to go into the part of the thermochemical equation. And notice I wrote the equation so there's only 1 mole of CCl4 because that's part of the definition of enthalpy of formation, is that we form only 1 mole of the substance. So another example problem. Let's use delta H now to find the enthalpy of a reaction. And we can use the tabulated values using this equation to find the enthalpy of an overall process or reaction that's occurring. So delta H of a reaction at 25 degrees Celsius, 1 atmosphere pressure, 1 molar solution, is equal to the summation, that's what this big fancy E thing looks like, or means, of the enthalpies of formations of the products minus the summation of the enthalpies of formation of reactants. So notice it's the difference. That's what the minus sign means right here. So always products minus reactants. So a little bit more about the words right here. So first of all, you have to look up these delta HFs in Appendix C or in your textbook. So that's where you find these numbers for the HFs. The N's right here and here in the equation stand for the coefficients in the balanced chemical equation. So if there's a 2 in the reaction, then you have to multiply whatever that reactant is by 2. And then the big capital E's, funny looking ones, mean add them up. They just mean add them together. So add together all of the products' enthalpies of formation, add up all the reactants' enthalpies of formation. So here's the example problem using this equation. calculate the enthalpy of a reaction for the combustion of 1 mole of C6H6. C6H6 is known as benzene, a real popular industrial chemical used to make lots and lots of polymers in the world, and it will produce carbon dioxide and water when you do this combustion. So step number 1 is to write the balanced chemical equation, and when you're performing a combustion reaction, remember you're always going to react it with oxygen, so C6H6 plus oxygen, because you need oxygen to perform combustion. And then we're going to make some CO2 over here, and we're going to make some H2O, and we want to know what is this enthalpy of this reaction. What's the delta H for? That's our goal. So we also have to make sure we want 1 mole, or we have 1 mole of this, because otherwise it's not the enthalpy of formation or combustion of 1 mole of this C6H6. We have to balance the equation where there's a 1 right here. So if I put a 6 in front of the CO2 right here and a 3 in front of the H2O, now I have 6 hydrogens and 6 carbons. But how many oxygens do I need here? There's 12 plus 3, so there's 15 oxygens on this side. What times 2 equals 15? Well, 7.5, right? So I'll write it this way. 15 halves would be the numerical value, and you can use halves, you can use thirds, you can use quarters if you need to balance something so a particular substance of interest only has a 1 in front of it for 1 mole. So now we can do the math part. The enthalpy of reaction is equal to the products minus the reactants, so these guys minus these guys right here, and numerically we will take 6 times the CO2, because there's 6 of them, plus, because remember we want to add them up, because that's what this little symbol right here means, or this big E symbol, 3 times whatever water is, minus the reactants, and the reactant is C6H6, so times 1, plus 15 halves O2, so 15 halves times whatever oxygen is. So now we need to look these up on Appendix C right here, and CO2, if I look that up, I've got it highlighted right here, is negative 393.5, so I wrote down negative 393.5, plus 3 times water. Water's over here underneath oxygen. I'm not sure why they put it there, but it has oxygen in it, and it's negative 285.83, so times negative 285.83. I'm just going to drop the units here for right now because we know all of these things are in kilojoules, so I'll put kilojoules at the end. Minus the reactants, and the reactant, one of them is benzene, and it's in its liquid form. If you see right up here, liquid form, and there's 2 different values, one for the gaseous and one for the liquid. We want the liquid one, 49, positive 49. 1 times 49 is 49. Plus 15 halves times oxygen. So oxygen is over here under oxygen, and it's oxygen in its gaseous form, and since it's diatomic, we'll look for O2, and that's 0. Oh, 0. That makes the equation easy. So 15 halves times 0 is 0, of course. And now we need to take our calculator and multiply these guys together. Add it to these, subtract 49 from that. And I believe if you end up doing all of this on your calculator, I'll save you the punching of the buttons, you end up with 3.267 kilojoules, and a negative sign right there, meaning that the process or the combustion is exothermic, and that much energy is released. So there's one example of calculating the enthalpies of reaction using the enthalpies of formation. So an interesting piece here was that oxygen has an enthalpy of formation of 0. So which others are 0? Which other ones on here are zeros? All right, if you have your textbook, take a look in the back in Appendix C and just notice there's 0, 0, there's a 0, there's a 0, there's a 0. Oh yeah, there's quite a few of them that are 0. Well, could you find a pattern of which ones have an enthalpy of formation of 0? Well, if you look at it a little closely, it turns out that all things in its elemental form are 0, as long as it's at 25 degrees Celsius and 1 atmospheric pressure. So what does elemental form mean? Well, if it's iron in its solid form, it's 0. If it's bromine in its liquid form, it's 0. Notice it's diatomic too, because that's how it fits in its elemental form. Hydrogen in its gaseous form is diatomic, and its enthalpy of formation is 0. But be careful, because bromine, if it's in its gaseous form, Br2 gas, has an enthalpy of formation of 30. So watch the phase and make sure that you know that it is the phase of matter it would be in at 25 degrees Celsius. So one last problem. Here is calcium carbonate, and calcium carbonate is decomposed into calcium oxide and carbon dioxide. And its enthalpy for this particular reaction is 178 kilojoules. Notice it's a positive value, so that means it's an endothermic process, meaning you have to put energy into this system to break it up into those two items right here. So here's the question. Use Appendix C to calculate the enthalpy of formation for calcium carbonate. So now it wants to know just this particular substance's enthalpy of formation. Since we're given the enthalpy of the reaction right here in the thermochemical equation, now we've got to find this. And if you look back at our equation right here, here's the thing we know. We know this from right here. We could find the products by looking them up in Appendix C, but the reactant's unknown, and so we're going to have to find that. So let's write down the equation right here. The enthalpy of formation of calcium oxide, I looked up in Appendix C right here underneath calcium, and calcium oxide is negative 635.5. And then the enthalpy of formation of carbon dioxide right here, I looked that one up also in Appendix C. It's negative 393.5. And then my equation will be enthalpies of the products minus the enthalpies of reactants. And I have the two products right here. And I have their values. So my enthalpy overall of the reaction is 178.1. My products will be calcium oxide, or negative 635.5, plus negative 393.5, because remember this symbol means add them up. And remember these are kilojoules as well, and so when my answer ends I'm going to be in kilojoules, minus the enthalpy of formation of the reactant. Since there's only one reactant right there, that's going to be calcium carbonate. I'll call that X, and that's the thing that I want to find. So now we have to do just a little bit of algebra, and we have to subtract or add these two together and then bring them to the other side of the equation to solve for X. And then if I solve for X, I should end up with negative 1207 kilojoules. And you can plug the number back into this equation to check it to make sure. So that's an overview of enthalpies of formation, the amount of energy that's needed to form something from its constituent elements. Good luck with your enthalpy calculations.